Hello and welcome to part 3 of my Code It Yourself role-playing game series. If you've not seen the previous episodes of this series, then I suggest you go and watch them because I'm just going to carry on directly from where I left off. And indeed, where had we left off? Well, we'd implemented some dynamic objects and we'd implemented the ability to script sequences and watch them play out on the screen. So here the character is now under control of the scripting engine, and we can see we've got other objects also in control of the scripting engine, and we've also got some dialogue being displayed. And one of the things that we got from the last video is that by using object-oriented programming, that adding new objects to the game was very simple, and they behaved appropriately without any additional coding from me. And so ultimately we've got the very basic scaffolding for a role-playing game, and this video is going to be about how do we start bringing it together to implement the game. So we are going to be adding a few more dynamic objects, and there's quite a lot of those, so I'm going to add them as and when we need them. And we're all going to look at the ability to change from one location to another. And hopefully by the end of the video we'll have a very simple system for the implementation of quests. But before we get started, I want to address an oddity of the last video, which was this line here, and I did apologise for it in the video. I needed to include it in order to make the video work on the limited time budget that I had to film it. And this is a rather unusual statement, so some of you may not have seen the inclusion of a CPP file before. But it works the following way. Firstly, you can include any file here. All include does is cut and paste text into that location in the compilation stream. And in this instance, we needed to include it to get access to this token here and fulfill it with some implementation. And unusually, because of the way I do things, we'd created a RPG main which included our override class of the console game engine. Let me just find it here. In a way similar to how my other videos work, I tend to do everything in one file, and so it looks a bit odd. And when we're working with object-oriented programming, in C++, it is a little bit bad form to do everything in a single file. So I'm going to start this video by quickly whizzing through all of this and extracting it into a header file and a CPP file. I'm going to call those engine.h and rpgengine.cpp, and we'll launch the game from our main file appropriately using the engine. So one moment please whilst I whiz through this at high speed. Perfect. I've now encapsulated everything that we've created in a class called RPG Engine and given it the .h and .cpp files. The functional code hasn't changed at all. So let's start by implementing the process that allows us to control the main character, Witty, from one map to another when he goes through this door. We want it to load the inside of this building. Knowing that I'm going to be using more than one map, I want to store maps as an asset. On the whole, maps won't really change, so I want to make sure I've only ever got one instance of them, in much the same way that we handle sprites. So I'm going to modify the RPG assets to also handle the loading of maps. I'll add a load maps function. In exactly the same way we handle the sprites, I'm going to handle the maps. I'm going to create a map of maps. And I'm also going to add a getter function for this too, so we can get a map by passing along a string name to identify which map are we interested in returning. In a very similar fashion to sprites, we're going to need to implement a load maps method too. So I'm going to create a little auto lambda function here to automatically load the map and name it for me. But I need to tell my singleton what is a map, so I'm going to include that up here. Let's just remind ourselves what the map class did. Well, it simply stored information that represented the tiles, and information that represented whether a tile was solid or not, and it created itself. It was a self-contained, fully encapsulated object. And if we look at the implementation of maps, we can see that for anything that derives from the CMap class, we override the constructor, and that's where we populate information about what makes that map unique. And also, if we remember from I think the first video, we created two village maps. Well, I'm not going to create village 2, I'm going to create that as being home 1 and village 1. And the idea being that we can enter the building that exists within the home 1 map. So in the constructor we call the create function, which will load the home.level data created by the external map editor. I don't want to use the village sprite sheet for this time. I'm going to have a special one called high tech. It's kind of like a laboratory. And I'm going to call this map home. Going back to our load maps function in the assets class, we just now want to call load, and pass in a newly created instance of each map that we're going to use. So we've got map village 1, and home 1. In the main engine's onUserCreate function, we specified the map directly. We set a variable mp_current_map to that map. Now instead of doing that, we're going to grab it from the assets just to make sure this works. And we're going to use the singleton directly. RPG assets. Let's get an instance of it. And we'll call the getMap function, and we want the first map to be Coda Town. We'll have to tell the singleton to also load the maps. So let's just see if that works. Perfect, it's loaded our map from the singleton. We need a way to transition from one map to the other. And the easiest way to do this within our current framework is to create a dynamic object which teleports the player from one map's position to another map and position. So let's take a map like I've drawn here, which is an empty map, except it's got a building in it. And we've specified some of these cells are solid, so the player can't walk through them. I'm highlighting those in red. What we won't do is specify this cell that contains a door to be solid, because we want the player to be able to step on top of that door. What we will do instead is specify that here we have a dynamic object, and we'll call this one a teleport. And so if the player interacts with this teleport dynamic object in any way, either by talking to it, or using the action button, or by stepping over it, we're going to have an onInteract function for this dynamic object. And that will allow the dynamic object to then go and coordinate the game engine to load the map that's required and relocate the player there. So along with this dynamic object for the teleport, we want to store a map address or name which represents which map are we teleporting to, and we also want some coordinates that represent the location. So let's just take a quick look at a secondary map. So let's say we've got some solid blocks here too, slightly zoomed out scale. We leave some here. This represents the doorway of the inside of that building. So in a similar sense, we want a dynamic object that represents a teleport here. So when the player interacts with this dynamic object, the player is going to be teleported to this location. And when the player interacts with this dynamic object, the player is going to be teleported to this location. And this way we can transition between maps. But this has also now introduced a new feature that we haven't covered yet in a previous video, and that is this ability to interact with things in the game. Now, because this is a big project, I'm not going to type out all of the code line by line, so instead I'm going to cut and paste and try and describe the bits that are relevant. I hope you'll forgive me in this sense. There's just too much code to start doing that, and we'll be creating videos until Christmas. And I really want to wrap this up in one more video after this. So here's the teleport dynamic object. It inherits from dynamic, and it overrides the drawSelf and update functions that we created in the previous video. The constructor of the teleporter takes the position of where this teleporter exists in the current map, it takes a string that represents the map to teleport to, and then it takes a target x and y, which is the coordinates of where to place the player once the teleportation has happened. And of course all we're going to store in this class are those coordinates, the x and y of the target map and the map name. Let's go and implement the body of this now. So the constructor, all that's going to do is cache a local copy of the data for that object. And because we want the teleporter to be able to be walked on top of, we make it solid against nothing. So the player, which is a dynamic object himself, can actually walk over this object. Dynamic objects are also responsible for drawing themselves. So in this case, we don't really want to see anything, but I'm going to leave it in that it draws a circle, and that's so we can see that we've put the object in the right place. When we come to release the game, we'll comment this out. And the teleporter object does nothing on its update function, it's just a static thing that fires an event, so we don't need to give it any behaviour. But how do we associate now the teleporter with the map? We can see in our onUserCreate function we've been doing this by hand, and we can no longer do this anymore. It's grown beyond this initial debugging stage. I think it's now time that we allow the maps to assemble their own collection of dynamic objects. So I'm going to add to the main map class an additional function called populateDynamics, and that takes a reference to our vector of dynamic objects that the game engine has. And of course I'm going to need to override that for both our village and our home derived classes. And this function means that whenever we load a new map, we can add the dynamic objects that belong to that map to the main dynamic objects container for the engine to process. So let's just move home out the way for now and focus on village 1. The fact that it returns something right now is irrelevant, so I'm just going to make that return true by default. But what I do want to add to this vector is the teleporter. So I take the vector that's passed in and I push to it a new set of dynamic objects. In this case it's the teleport object. I'm setting it to be position 12 and 6, and I want the target map to be called home, which you'll have noticed is the name of our other map. And the location within that map I want to go to is 5 and 12. We can work out the coordinate where we want to place the teleporter by using the map editor. And we can see here it's 12 and 6. So this is the location we're going to put our new dynamic object. Likewise, going back to the home, I'm going to add 2 teleporter objects. They're next to each other. So the locations on the map are 5 by 13 and 4 by 13. So they're next to each other in the x-axis. But they both teleport to Coda Town, which was the name of the original village, and they teleport to the same location. Looking back at our onUserCreate function again, we can see that where we were handcrafting this construction before, we're now going to leave that to the maps. So it's time to remove all of this and create a change2map function. So in the header file for the game engine, I'm going to add the function changeMap, which will load up a new map and position the player at the required location. But there's a process involved when changing maps. The first thing we'll want to do when we change maps is destroy all of the dynamic objects in our vector of dynamic objects. So I'm going to clear it. And we'll improve this later by deleting the objects that we've created on the heap. But since we've just cleared the vector, I also want to add the player back to it, because remember, the player is always going to be the first object in our vector of dynamic objects. The name of the map has been passed into the function, so I'm going to use the name as an index into our asset singleton to get the new map. And we'll set our current map variable accordingly. I then want to update the player's location to wherever was requested. I want to then populate the map with the dynamic objects. So the current map, which is the new map the player has just been teleported to, I'm going to call the populate dynamics function, which will then append to the vector of dynamic objects our teleporters in this instance. Back in the onUserCreate function, I no longer need to create my 2 skeletons. I'm going to get rid of them for now. And I now know that my change2map function is responsible for populating my vector of dynamic objects, so I don't even need to do this. I still need to create the player as a dynamic object, so I'm going to leave that bit in. And the current map is also no longer relevant, so we'll get rid of that. And we'll use our new changeMap function to initialize everything for us. To begin with, I want the player to be in Coda Town. And I know, looking above, that the location is 5 by 5. So I can remove this as well. Let's just see if that does indeed load the map. It has, and even better, we can see it's drawn the teleporter object with a circle. If you remember, we told it to draw itself by drawing a circle there. Perfect. But how do we check if 2 dynamic objects interact with each other? Well, we need to go back to the core of our physics engine. Right now, it's set up to check whether the objects interfere with the map, and if it does, it positions them and handles the response accordingly. But all of that code only worked for static map collisions. I'm going to add some new code now to handle collisions between dynamic objects, and we're going to assume that they're also 1 unit wide by 1 unit high, like everything else in the game. But the main difference here is that dynamic objects are not always going to be bound to an integer boundary within the game space. So in this loop, where I'm looping through every dynamic object, I'm going to have a second loop, where I'm also going to iterate through every dynamic object. On the whole, we know there's really not going to be that many dynamic objects within a given scene, but the reality is in most cases it's going to be perhaps 5 or 10 dynamic objects per map. We want to make sure that the collision isn't being tested between the dynamic object to be tested and the original dynamic object. There's no point in checking does an object collide with itself. Once we have determined that a valid collision can occur, we're going to use the solid states of the two objects to work out whether we should carry on checking if they're allowed to interact or not. So if both of the objects are considered solid against dynamic objects, then they must not be allowed to overlap. But if either one of the objects is basically transparent to dynamic objects, then they can overlap. We'll come back to solid versus solid dynamic objects later. But for now, we want to overlap with our teleporter. I don't care about things like enemy creatures and other things in the game overlapping with most of the dynamic objects. In fact, I really only care what the player is interacting with. So I'm going to make sure that the object under test is indeed the player object, which we know is the first element of our vector of dynamic objects. And given that all of our objects are unitary in width and height, I can do a very simple rectangle-rectangle collision to check have they indeed overlapped. And in this instance, I'm just taking the coordinates of my base dynamic object and I'm comparing it to the coordinates of the target dynamic object. And if this returns true, then they have overlapped. Just throw a quick comment in here so we can keep track of things. So the object is a player and it's allowed to interact with things. So if the player has overlapped a dynamic object, I want it to do something. And I'm going to first of all check, is this something that is map related? Which means we're going to need a new function in our map class. I'm going to add in a function called onInteraction, which again takes the vector of dynamic objects. It also takes in a pointer to a dynamic object, which in this case would be the player, but it could be something else that's been triggered by the interaction testing. And I'm also going to pass in what is the nature of this interaction. And to keep the code a little bit readable, instead of just specifying a number there, I'm going to throw in a little public enum, talk or walk, and we can use that to differentiate between the player interacting physically with an object or just walking on top of an object. This of course means we also need to implement our onInteraction in our subclasses. I'm going to start a convention that if there is a successful interaction, that this function returns true, otherwise it returns false. And right now, even though we've just added the nature of the interaction, it doesn't matter for a teleporter. In any way that the player interacts with it, I'm keen to do something. When we defined the cDynamic teleport subclass, we gave it a name. We called it teleport, which means we can identify what dynamic object was interacted with. So in this instance, if the target's name is teleport, then I want to somehow call the changeMap function in the main game engine. Fortunately, we already have a process to do this, but we need to modify something ever so slightly. We could script it in as a scripted sequence. We only have two commands at the moment, command move to and command show dialog. Let's create another one, which is changeMap. And in this instance, it looks very similar to our dynamic teleport function. It takes the same properties. But if you remember, the start function is what we're going to be overriding when this command gets called by the script processor. Let's give this new command some body, so the constructor is just going to store the name and the position where we're going to teleport the player to. And the start function, the bit that does the business, is going to call the main game engine changeMap function, which we created earlier. Then it's going to mark it as completed, so the script processor will reject it. So this command will happen almost instantaneously. And it's quite useful to have a command like this, because you could imagine a cut sequence which takes place over several maps. You'll need to change them somehow. So going back to our map where we're handling this interaction with the teleport, because the teleporter contains its own information about how to perform the teleportation, we don't need to look for specific names of teleports, it's just a teleport. Whenever it happens, we want to add a command to the script processor queue. And so the command in this case looks a little bulky because we've got some casting going on in here, but you can see we take the global pointer to the script engine and we add to it our new command with the relevant parameters. But, and because adding a feature like this is a never-ending rabbit hole and it makes for very embarrassing video making, we also now need to expose the script processor to our maps. So let's make a change to the base map class that allows it to be aware that the script processor exists. And in the base map class, I'm going to add a static pointer to the script processor. I'll need to give that some definition in the maps.cpp file. I'm just going to remember to set this to public, so we can actually access it externally. Now, in much the same way that we set the game engine to be accessible by the commands, we need to do the same for the script engine. So we'll find our public script variable and we'll set it to the address of our scripting engine. There's only one last thing to add before we continue, and that is the onInteraction function for the Home1 map derived class, which you can see is exactly the same. If there is a teleporter, it just deals with itself and sorts itself out. Going back to the main game engine now, we can actually implement what happens when the two dynamic objects interact with each other. And we want to check the map to see if the map is interested in that interaction. So here I've got Witty walking around the map. We're going to go and interact with the teleporter. You might see that the collision detection there is a little bit sticky. We might adjust that in a minute. But let's put Witty into the oh, hang on, something very strange has happened here. Well, we can see that Witty's location changed, but the map isn't being rendered correctly. But two more teleport circles have appeared. In fact, if I walk back into those, we're back into the normal map. So it looks like it might be working. However, it's not loaded the map correctly. Let's investigate. And the problem is here. When we entered Home 1, it loaded the level correctly, but it couldn't find the sprite High Tech. We don't really have any error checking on this project. That's just to keep the code as clear as possible. But this is the kind of thing that we might want to actually throw an exception for when the game starts. Needless to say, adding High Tech to our list of loaded sprites is very simple indeed. Done. Let's try again. So I'm in control of Witty. We walk him over to the teleport, and we've loaded a new map with a new tile set. We can walk Witty back. Great. And go back and forth as much as we like. And we'll try the other teleporter in this room, and there we go. So we've handled local map to local map navigation. Now I just mentioned that the collision detection was getting a bit sticky, and that's because we don't handle Witty like we handled Jarrio. Jarrio relied on acceleration, which meant on a reasonable frame rate, the actual amount that Jarrio moved per frame was very small. And if you remember, we didn't quite test a whole cell. We would test, depending on Jarrio's origin point, which is going to say about here, we would only test about 0.9 in this direction, and the whole 1.0 in that direction. And this made sure that the object that represented Jarrio was slightly smaller than the gap it was trying to squeeze into, and this worked very well. But for Witty it doesn't work because we don't really use acceleration, which means Witty's movements are a lot more discrete around the map, and that's why it takes a bit of effort to find the sweet spot that allows Witty to enter the constrained solid map tiles. Now, because precision platforming isn't the name of the game when it comes to a top-down RPG, what I'm going to do is, instead of representing a contracted border like this, all dynamic objects are going to be represented, instead of one by one, they're going to be pulled in a little bit. So if we say that this was our original dynamic object boundary, which is 1.0 and 1.0, in reality what we're going to be checking for is some inner boundary that is smaller than a unit square. So in that case, all objects can fit within adjacently spaced solid tiles, which means I'm going to have a fixed border in from the object. And so I'm going to change our collision detection code to take into account of this border, and I'm going to hard code the border. I'm going to say 0.1 to begin with. And if we test that, we can now see that the collision system is a lot more relaxed about allowing Witty to enter single square gaps. Since we have a populate dynamics function now as part of our maps, we don't just have to add boring things like teleporters, we can also add enemies which would be common to this region, and indeed right now they would respawn each time that the map was loaded. We'll come back to persistence in a later video. But let's have some fun. Let's add some skeleton characters that we created in the first video to this map. You'll see I haven't created the object yet, and that's because in the first video we created a skeleton just by implementing a dynamic creature object directly. I think now it's time that for different types of enemies and creatures we want them to have their own objects, because we'll be able to script their own behaviour in that way. Let's start with the very basics. We'll create the object and we'll give it a constructor. I'm going to give our dynamic creature Skelly object an implementation for its constructor, and this is where we'll take the opportunity to give it a name. We'll call it Skelly, and we'll also grab a sprite sheet as we did before that represents what this creature should look like. We'll also set the health and max health properties, and I don't think skeletons are very friendly, so we'll set that to false. Now all of the other functions about how to draw the creature were contained within the base class, so we don't need to reprogram those. If we go back to the maps where we're populating the dynamics, we can see, well, the map is happy with that too. And if we take a look, we can see it has randomly placed 3 skeleton objects within the map. They don't do anything yet. That's because they're stupid. They don't have a brain. They have no way of implementing behaviour. We know we can command them with the script processor to walk around, but they don't have any choice but to stand still right now. So how do we give these creatures a little bit of AI? Well, looking at the dynamic base class, we know they have an update function, so we know there is a facility to actually implement behaviour. Specifically though, creatures may have an AI type behaviour. Most dynamic objects might just change what they look like, but for creatures we want them to do something a bit more sophisticated. So in the base class dynamic creature, I'm going to add another function which is to be overridden by subclasses called behaviour, which means in our Skelly class we also need to have the function behaviour. For the base dynamic creature class, its behaviour does nothing, we're not interested. But we do want this behaviour function to get called. And the only thing that we know is called on every single frame is the update class. So let's add to our update class at the end a call to behaviour. And we want to pass in the elapsed time and our player pointer. Now, the eagle-eyed amongst you will have noticed, hang on, what's this player pointer? Where has it appeared? That wasn't in the first video. And you're quite right. When I went away to think about what dynamic objects might require, I thought actually most of them will respond to the player in some way or another. So I wanted to include a pointer to the player's dynamic object in case that interaction needed to occur. And this is a good example of why this might be a useful thing to do. We want the skeletons in this case to attack the player. So they're going to have to walk towards the player. They need to know where the player is in the game engine. Going back to the dynamic creature update function, it will call a behaviour function, but it will call a behaviour function of whichever object is the subclass. So in this case, even though this function is fulfilled by dynamic creature, it will call the behaviour function of the skeleton if the object is a skeleton. And this is polymorphism, and this is why object-oriented programming is very powerful. So I'm reusing code all over the place, and you'll notice that each time I add new objects, all I'm really doing is adding a constructor and overriding 1 or 2 methods. So let's have a think about our skeleton's behaviour. Because we've passed a player object in, we can do some interrogation of what is the relationship between the skeleton and the player. And the relationship that I'm most interested in right now is the distance between the two. So I'm just going to use Pythagoras' theorem to calculate what is the distance between this skeleton object and the player. And I can check that if the distance is less than a certain amount, then I can set the skeleton's velocity parameters to make the skeleton walk towards the player. In this case, I'm taking the difference that I used as part of the Pythagoras calculation and normalising it, so I've got a unit vector for velocity, and I'm setting the velocity speed to 2. If the player is further away than 6, then I just want the skeleton to stand still. A very simple behaviour. Let's see what that works like. Well, I'm in control now, and we can see there's 3 skeletons, and I'm going to edge towards this one. Now, we've entered the radius, and you can see it's following me around. And it's completely animated on its own accord, and it's doing the directional changes of its own accord, and that's because we're using polymorphism in this instance to handle all of that fiddly stuff for us. We can also see that because we've set the dynamic objects to be, in this case, solid against the map, that it can't pass through them, which is also a desirable property. Even though we've not explicitly coded that in, the game engine has handled it for us. We do see some undesirable things though. The dynamic objects are going on top of each other, so it now looks like we've really just got 1 skeleton, where we should have 3. And also, it seems to get quite skittish. The objects are jumping around a fair bit. And that's because it's making decisions too frequently. Effectively, our skeletons are making a decision every single frame, and unless you're into speedrunning, it's very difficult for normal people to do a decision at 60 frames per second, for example. It's very possible that all of our dynamic creatures are going to need some sort of AI, so I'm going to alter the dynamic creature base class to include some utility variables to help us implement an AI. And in this instance, I'm going to create a variable floating point called stateTick. And the idea of stateTick is it's going to deplete every frame, and when it becomes less than or equal to 0, the AI is going to make a decision about what it's going to do. And once it's made that decision, it will also then reset this state tick variable. So in this way, we can have the AI make a decision every 1 second, or every 2 seconds, or every half a second, instead of being every frame. So going back to our skeleton implementation, let's set that variable to something sensible. So to begin with, let's say we only want the skeleton to make a decision about anything every 2 seconds. In the behavior function itself, we're going to reduce the state tick variable by f-elapsed time. And only if the state tick is less than or equal to 0 do we actually want to do anything that changes the current operating state of that dynamic object. And we must also then reset the state tick variable. In this case, I'm going to set it by adding 1 more second. So to begin with, the skeletons won't do anything for 2 seconds, but then after that, every 1 second, they're going to make some sort of decision. Let's see how that works. So the skeletons won't do anything to start with, but now we can see that once they've made a decision, they stick with it. They're still overlapping though. Let's see if we can sort that out. And the reason they're overlapping is because in that event of 2 solid dynamic objects, we don't do anything. We just allow it to happen. I'm going to resolve the collisions between dynamic objects in exactly the same way I'm resolving them between the dynamic object and the map. The only difference is here is when there is a collision, instead of using integer rounding to locate the object in the right place, we need to look at the dynamic object's properties and decide what is 1 unit to the left, or 1 unit above, or 1 unit to the right of the dynamic objects that have collided. Again, I'm going to check if the bounding rectangles overlap. And if you remember with Jareo, checking horizontally before checking vertically is very important, or else things get stuck at the diagonals. So we'll first check to see what's the horizontal situation and resolve it. And so if there is a collision, we can see that the dynamic object's position, where it's going to become, is set to the object that it's collided with at plus or minus 1, depending on which direction the base object is travelling in the first place. Once we've done the collision detection for horizontal, we then do collision detection for vertical. So let's see how that looks. Well, if we tempt a skeleton out of his hiding hole, here we go, we can see firstly Whitty and the skeleton can't overlap each other. That's very nice. So the collision detection is working on a dynamic object versus a dynamic object. Let's pull some more skeletons into the arena. Now they still got to obey the rules of the map as well, but nicely this time they're not overlapping. They might be competing for space, but they certainly don't interfere with each other. And we'll probably end up in a situation where the player becomes boxed in. So far, the only form of interaction we have is when the player overlaps a dynamic object. But what if the player actually intended to interact with something, i.e. it uses the action button, we'll call it the spacebar in this, to perform an action, either attack or read a signpost, open a chest, activate a switch. Well, let's get rid of our little script testing code and do something when the user presses the spacebar. In this instance, we want to interact with the object that's in proximity to the player. Here we've got 2 dynamic objects. One's the player and one represents a signpost. So I don't know, we've not implemented that dynamic object yet, but let's say it presents some information to the screen when the user interacts with it. To check for interaction, we want to see what's adjacent to the player, and the player will only face one of 4 directions: north, south, east or west. So in this instance, we can set out 4 probes to see if there is a dynamic object that lies beneath the probe. So if the player is facing north, or upwards in this case, we'll set a probe to be here. Likewise, south will be down here, west and east. And what we'll assume is that these probes are positioned 1 unit away from the centre of the dynamic object. We already store facing direction as part of a dynamic creature object. We just don't expose it in the class. So I'm going to add that function in. And this one's so simple, I'm just going to make it immediately return mn facing direction. So now, when the user presses the spacebar, we can use the direction that the player is facing in to determine this position of a probe. So we'll call our test point test x and test y. And depending on the facing direction, we want to offset test x and test y accordingly. There's a little error here, and I think it's worth discussing. It says that get facing direction is some sort of a problem. If we look at the error, class CDynamic has no member get facing direction, and that's true. That's because we've added it to the CDynamic creature class. We don't really want to be putting casting in at this point, and we know that the pPlayer object is always going to be of type dynamic creature. So In our rpgengine.h file, I'm going to change our pPlayer object from type CDynamic to CDynamicCreature. Once we've got the location of the probe, we then have to test it against all dynamic objects to see if it has hit one of them. I'll use a little iterator to go through the list, and this is just a case of checking to see is the test coordinates within the bounds of the dynamic object's rectangle. We'll assume for now that the player can really only interact with friendly things, so I want to check that the target is friendly. Because if it's not a friendly, then the interaction would be an attack. And we'll worry about attacks in the next video. In the same way that we checked for two overlapping rectangles for dynamic objects and called the walk interaction, in this case we're just going to call the talk interaction on the map. So how can we test this? Well, in the home map, I'm going to add another object, something that we can talk to. And I'm going to call this creature Bob, and we'll just make Bob look like a skeleton for now. I'm going to set Bob to be positioned at 12 across and 4 down. And we'll add Bob to the vector of dynamic objects. Because Bob hasn't been given a special class of his own, and he's just a dynamic creature, his animations will work, but he has no behaviour. There was nothing specified. But we want to check if the player can interact with Bob, and we'll let the map handle this interaction. So in this case, if the target's name is Bob, then we want to do something. We'll display some dialogue. And in the last video we showed that we can wrap up commands in a macro to make them a little easier to read. So let's see what happens when we go and interact with Bob. Firstly, let's get to Bob. I have to draw these skeletons out of the way first. Right, let's go back in. So we've entered, there's Bob. Bob's a skeleton, but I don't fear him, he's not going to attack me. I can't walk in or over Bob, but I'm going to interact with him by pressing the spacebar. Hello, I'm Bob. So we've now created a framework which is very simple to add interactable events. What's interesting in this case is it is the map that handles the event. But a map should be a fairly static thing. What if Bob was part of a quest and needed a complex chain of events to decide his actions and his dialogue? Well, this implies we need an interaction layer, one up from maps, to handle quests. So let's look at the chain of events that needs to happen and in which priority when an interaction occurs. So we'll know we've got the player is going to interact with Bob. The first thing we might want to check is the dynamic creature that represents Bob. We'll give that an onInteraction function, like we have with the maps. If the dynamic creature is not interested in that interaction, then the next thing that might be interested in is the quest. We don't have a quest object yet, but let's assume that we do have something, then we can also call the quest's onInteraction function. In fact, what we may find is we've got numerous quests on the go at any one time. If none of the quests are bothered about the interaction, then the only thing left is the map. And so we'll make sure that our onInteraction functions return a boolean, true or false, to say whether they have processed this interaction and it should be or should not be continued further down the chain. So if the dynamic creature says false, I'm not interested in that interaction, it then moves on to the first of the quests. If none of the quests are interested, it then moves on to see if the map is interested. So what's going on with these quests? Well, I'm going to create a quest object, and I'm going to create a list of quest objects. And to this list, I'm going to add one quest, which is going to be my base quest. This is the overall game quest. Completion of this quest signifies that the game has finished. All of the other quests are granted to the player as they proceed through the game. And typically, the most recent quest added to the list will on the whole be the one the player is most interested in solving. Not always, but mostly. And so as the player accumulates quests to solve, the list grows. And as they slowly tick off the quests one by one, we end up with just the base quest left. And it's important to always have a base quest, because when the game starts, that's all there'll be is a base quest. It's just the condition for finishing that quest won't be possible. By encapsulating quests in a single object in this way, we can store the game state. We can save to file, as the only variable information in the game will exist within the quests. We'll make sure that maps are just static. Yes, they contain some rudimentary dynamic things in order to help the player throughout the game, such as signposts and teleporters and other bits and pieces, but fundamentally it is the quests that contain the dynamic information that really represents the current state of the game. And by maintaining a list of quests in this way, saving and loading the game is quite trivial. We can just serialize the quests to disk and then read them back again and repopulate this list. The second benefit to having a quest encapsulated is we can add lots of interesting functionality to a quest. So decisions that get made to decide how the quest pans out can be stored as local variables, as can quests such as please collect 10 dead skeletons. It's in the quest itself we can store the value that records how many skeletons we have collected. As quests are quite fundamental, I'm going to create two new files, rpgquests.h and rpgquests.cpp. The definition of the quest is quite simple. It is of course going to be just a base class. And it shares lots of properties with things we've seen already. We've got an onInteraction function. We've got a populate dynamics function. Now that's quite important because we might want certain dynamics to only appear when a quest is available to solve. And this way we can implement puzzles and locked doors and that kind of thing. Quests also need access to the dynamic objects, and they need access to the script processor. In fact, they also need access to the RPG engine itself, so they can issue commands. What we're beginning to see here is a bit of a pattern of similarity. We're seeing lots of objects with the same properties, and this is always an indication that our object-oriented design could be abstracted even further. And indeed, it seems to be the case that most of the significant objects in the game have an onInteraction, populate dynamics, a name, and links to the script processor and the game engine. I'll think about encapsulating that for the next video. So the base quest does nothing interesting at all. It just has blank implementations of the two functions that get overridden. In the quest.h file, I'm going to define our first quest, and just because we're testing, I'm going to call it testQuest. Quests have an additional Boolean variable stored in them to say whether or not they are completed, and we're going to maintain our quests in a list. I'm going to add quests to the main game engine, and I just simply need a standard list to pointers of quests. In onUserCreate, where we're creating the initial conditions for the game, I need to now create an instance of this quest and add it to the list. And I'm going to do that just before I create the player. So new cquest test quest. Now we've just decided that quests can also populate maps with dynamic objects, so we'll also update our change map function. And once we've added the dynamics from the map, we're going to add all of the dynamics from all of the quests that are currently in the list of active quests. And the populate dynamics routine for a quest also takes in the map's name. So the quest itself can filter out which objects do I need to add to this map. So let's create now a little quest where we've got a character outside of the house that you need to talk to before you can talk to a character inside of the house. If we go to our maps, we're currently using the map to place the object Bob. I'm going to disable that for now. And also, I don't need to add the creature Bob anymore, because we're going to make Bob owned by a quest. So we've only got the one quest, testQuest. If the map that we're populating is equal to CoderTown, then we want to populate it with Bob. Bob's going to sit outside. And we'll populate Bob at being at 6, 4. Hopefully that's not going to be in the middle of a building. I'm going to add a private variable to our test quest, which is unique to this quest, and it's going to allow us to keep control of what's going on in this quest, and I'm going to call it phase, so we know where we're up to. So if the map is CoderTown and the phase is 0, then we're going to display Bob. However, if the map is home and the phase is 1, then we're going to display Bob in his home. So let's see what happens now when the user interacts with Bob. We can check for this by looking at what the target is. If the target that's being interacted with is Bob, and this quest is interested in that, we can check for it. Then we can also check, during this quest, what is the current phase. Well, if it's 0, we'll get Bob to say something. Hello, you are in phase 0 of this quest. That's going to be the first dialog box. The second dialog box will be, you will need to, make sure we don't go too long, speak to me inside. And once this event has occurred, we want to return true, because we're done with it, we've processed it. This particular instance has now happened. We don't want the interaction to propagate any further down any of the quests, because there may be other quests that respond to Bob later on. We'll also set the phase to 1. So now we'll do something similar. Phase 1, we know Bob will be inside this time. So now we'll get Bob to say, you are in phase 1 of this quest. And that just returns true. It is possible at this point we could say the quest has been completed. But let's see how this works out. Now back in the game engine, where the user has chosen to interact with something, we need to check if any of the dynamic objects related to the quests are being interacted with. So I'm going to iterate through them using little OR list, and we check them quest by quest. And if any of them return true, I'm going to set a boolean flag to true and break. So the first quest that is happy to accept the interaction and deal with it will stop that event from propagating forwards. So let's see how Bob moves around depending on where the quest is currently up to. So there's Bob currently in the village map. We'll go into the house and we can see Bob isn't there because we're only in phase 0 of the quest. Let's move back outside and we'll go and interact with Bob. Spacebar. Hello, you are in phase 0 of this quest. You will need to speak to me inside. Fair enough, Bob. Let's go and have a look inside. Ah, there you are. You've appeared. And just before we go and speak to him, if we go back out now, you see Bob has disappeared. He's gone inside. And we can speak to Bob. You are in phase 1 of this quest. Very nice. We need a way to give the player new quests, and I'm going to make that scriptable, because that's the most common way you get quests in a role-playing game. For example, let's say we talk to Bob, and Bob says, please get me my widget of wisdom from Mount Doom, or some other poetic RPG nonsense. Then at that point we want to add a new quest to the list of quests that the player is embarked upon. This means we need a command called addQuest. And the implementation of addQuest is also very simple. It calls a function that we've not created yet called addQuest on the game engine. So let's add to the game engine another function, addQuest, that takes a pointer to a quest. And all this addQuest function does is push the quest to the list of currently active quests. We will at times need to expunge quests that have been completed from this list. And so I'm going to use a little bit of standard library loveliness to do just that. We use the removeIf function, which is part of algorithm, to go through the list and checks for any quests that have the BeCompleted flag set to true. From that point, we erase those quests. Now we can start to play with layers of quests. And I'm going to get rid of test quest now and change that to main quest. So this is going to be the one that always exists throughout the game. Let's add a character to our main quest. So the main quest is now placing the character Sarah here in purple in village map, and it places Skelly, or Bob, in the home map. I don't have any interactions defined yet with Sarah. But in the main quest on interaction function, I am going to add a Sarah response, and it's going to be show the dialogue, and I'm going to start putting the characters' names in so it's a little bit clearer what's going on. I will do that by saying Sarah as the first line. You have no additional quests. I'm now going to add an additional quest, which is going to get given to the player when they interrogate Bob. So we'll call this one Bob's Quest. For now, Bob's Quest isn't going to implement any dynamics at all. It's just going to handle interactions. So when Bob's Quest is active, when you interact with Sarah, we're going to get Sarah to say, you are doing Bob's Quest. But we need to get Bob to issue the original quest, and this can happen in the main quest. So if we interact with Bob as part of the main quest, then we can call our command addQuest, which takes a pointer to the new quest, which in this case is going to be Bob's Quest. But we'll do some dialogue first, just to give it some flavour. So the character speaking is Bob. I need you to do something for me. We'll have a second line, because I've got to fit it in somewhere. Predictably, there are rats in my basement. The obligatory first quest of any self-respecting role-playing game. So we can start to see where game design becomes a little bit complicated. The game designer needs to think about all of this and how it all interacts with each other. But fortunately, because we've encapsulated a lot of it, it becomes a much simpler task than having a whole smattering of variables across the whole program. So let's now take a look at the quest priority system in action. We can talk to Sarah, which is the main quest, and she says, you have no additional quests. Let's go and enter the building and speak to Bob. Hi Bob. Bob, I need you to do something for me. Predictably, there are rats in my basement. Well, Bob has now issued us with a new quest. And Sarah's still there, but now her response is, you are doing Bob's quest. It's no longer the default message supplied by the main quest. So the quest has taken control, it's taken priority of what events and what are the nature of the interactions going on. Admittedly, this video has been quite complex, but it's got some very important issues out the way. We're handling quests and we're handling navigation of the player around the world, and we've created new dynamic objects to help us do this. In the next video, we'll be looking at combat and items. A preview here, I can select I need to heal myself to get back up to full health, and that should enable me to have the beam sword. There we go. And we can kill things and interact with other things on the map. Let me just pick up a health. There we are. I can get my beam sword back. Perfect. I don't like killing the green things, they're too nice. Anyway, if you've enjoyed this video, big thumbs up please, have a think about subscribing. Obviously make sure you've watched the other parts of it first. Come and hang out on Discord, we're still looking for artists and plot designers and everything to work on the very final build of all of this, and I'll see you next time. Take care.